these collaborators, and we are interested to find some special surfaces in this ambient space. Maybe starting from Lancret problem for curves, asking to find those curves for which tangent line make a constant angle with a fixed direction, we can pass the problem to surfaces, asking to find those surfaces for which normal make a constant angle with a fixed direction. In Euclidean space, this problem has also some physical interpretation. It's about a paper of Cermele and Scala, saying that this problem comes from a physical problem in theory of liquid crystal, and another interpretation is a shadow problem. And maybe it is a natural question to ask generalization of this problem, so to find constant angle surfaces in other spaces. So today I will speak about these surfaces in S2 cross R, H2 cross R, and R2 cross R, but there are some classification in other homogeneous three-dimensional spaces, namely in the Heisenberg group, Nil 3, in the Sol group, Sol 3, also in other three-dimensional spaces like work products R cross R2, and from here to the hyperbolic 3 space, and also in Minkowski space R3 3 1. And maybe this topic is quite different from those we heard here, and I want to point it also the attention for this very recent paper I've submitted on arXiv a few days ago, and maybe here is the only one place where the word conformal appears. And so what is the goal of this problem is to find the explicit embedding equation for these surfaces. So a general theory could be developed, but we are interested to find explicit equations. This means we can find special coordinates, and starting from there to find explicit equation for these surfaces. And main property of these constant angle surfaces is the following. So if this is the surface M, and if this is dt direction, so by the way, the angle is measured between the normal and this special direction, the second factor of this product. So the angle is measured between the normal of the surface and it will here theta. And if we project this fixed direction onto the tangent plane to M, we have here, let's call it T. And the main property of this surface is that T is principal direction, and the corresponding principal curvature is 0. And our question was to find, so to classify those surfaces for which T remains principal direction, but the corresponding principal curvature is different from 0. So it's a kind generalization of constant angle surfaces. First answer is given in S2 cross R in 2009, and I will speak only very few words about this, and I will pass the problem, the mainly problem on H2 cross R ambient. So first, there is a characterization of these surfaces. T is the principal direction. I mean, this T, this projection, is the principal direction, if and only if M is normally flat. This means the normal connection is vanishes. And the equation are as follows. So M is this surface, and S2 cross R is embedded in R4. So we have 4 components. The last one is the integral of sine of theta, and the other 3 functions, the other 3 components are given by this this relation. And this function here is has this quite complicated expression. So let me pass to the other ambient to give more details to in H2 cross R. So to fix some notation, M tilde is the ambient, the product metric, the Levi-Civita connection, this the tangent line to the second factor, the curvature tensor, and we denote by F the immersion. Xi is the unit normal with the shape operator A. G, the metric on M, the restriction of the ambient metric with corresponding Levi-Civita connection nabla. And recall the Gauss and Weingarten formulas. Here H is the second fundamental form, and here nabla perp is the normal connection. Okay, so as I said, T is the projection, and theta is the angle between the normal and this dt. Recall the equation of Gauss and the equation of Codazzi, and we can compute the curvature, the Gaussian curvature of the surface. The first remark is that computing T, we have this equation, and computing the derivative of cosine theta, we have equation 2. And from 2, if theta is a constant angle, then we have either T is 0, which is not so interested, but it is in fact it's H2, and if theta is different from 0, we obtain from here that T is the principal direction with the principal curvature 0. So asking our question, we obtain first. So we will find some coordinates such that dx is in the direction of t. We will use the paper of Daniel Benoit, and in fact, there are 2 papers in which he constructs such kind of coordinates. And the first remark, we imposed also only dx is in the direction of t, and we obtain the metric in this form and the shape operator in this form, and the relation between theta and beta is this complicated partial differential equation. But we do not claim yet that t is a principal direction. If we do so, we can construct these coordinates x and y, and the expression of g and the shape operator a simplify. Also, the relation between beta and theta, and moreover, we remark that the angle function depends only on the first coordinate x. So a remark is for every two functions, theta and beta, satisfying these two previous conditions, we can construct an isometric immersion of M into H2 cross R with the shape operator defined as before, and such that this T is principal direction. So we will call these X and Y canonical coordinates. They are not unique, but they are related to these canonical coordinates are related by this expression. So in fact, this is more or less unique. It's up to translation and to change of sign, but Y is quite arbitrary. We will take into consideration the Minkowski model of the hyperbolic plane and the Lorentzian metric of the R3-1. A similar characterization as in the ambient S2 cross R, T is the principal direction if and only if M is normally flat. And now the classification theorem. I want to point the main difference between this case and the ambient S2 cross R. So at a certain point we obtain ordinary differential equation, which in the spherical case has only one solution, and in our case it is more complicated and has three solutions. And for this reason we obtain essentially the same form, but with three different types of equations. So we obtained in fact three types of surfaces. So this is the first version of this classification theorem, and it is used in order to find the example. A more geometric will be the second version. By the way, this is joint work with Frankie Dillon and Anna Nistor from Catholic University in Leuven, Belgium. So this is the case 1, this is the case 2. They look more or less the same, but they correspond to two different situations in the fourth component is the primitive of sine theta. The first three components are a combination of hyperbolic sine and hyperbolic cosine of a primitive of cosine theta. So as I promised, the second version of this theorem, which is more geometric. So this is the same. We denote by phi of x the last component, and this A, which is A1, A2, A3 from here, and the same for B, is a regular curve in de Sitter space. B is a regular curve in hyperbolic plane, such that they are orthogonal and their tangent are parallel. And this curve phi high is a regular curve in S2. The interesting problem is that for different surfaces we obtain different interesting curves. Here we'll see some examples. And moreover, if we reparameterize this curve by arc length, and we still obtain canonical coordinates, and the curvature of this curve is a derivative of our angle. Also, we have a third version. This we remark that the surface is constructed by using two curves, but we can construct the surface by using only one curve. So in fact, we have a curve and it's normal. And some examples, we obtain some rotational surfaces. For example, taking in the first version, we had a certain point, we have a function psi, and if we take this function, for example, 0, we obtain rotational surfaces. Other example, in the third case, if we give particular values for the constant vectors, we obtain this example, which is essential. We will see later. And finally, if for the angle equals x squared, we have this example, and this corresponds for the curve phi high as a Cornu spiral. I have 5 minutes, 3 minutes, okay. And we are interested also in minimality and in flatness, and we obtain this embedding equation, and for the flatness this embedding equation. So we obtain explicit surfaces. Okay, one more. So also in for the other model is done by Nestor, and to finalize, we did the same thing, the same mechanism for Euclidean space, and here we have two cases. This general, which is a generalization of constant angle surfaces, and here are especially kind of cylinders. And again, we obtain minimality and flatness. So we obtained other class of minimal surfaces in Euclidean space. An interesting result is, for example, this. So we obtained, in fact, another geometric characterization of the cathenoid. So it is known that it is the only minimal rotational surface, but with our notions, it is the only minimal surfaces having a canonical principal direction. And the flatness, and this one. Okay, thank you.
Questions? I have a quick question. Do you think about generalizing to higher dimensions?
Yes, for constant angle surfaces is already done in Sn cross R and Hn cross R. So maybe the next point is to see if we can pose the problem for the same ambient spaces. And for example, for in the Heisenberg group, T is no longer principal direction. So it is not for every three-dimensional homogeneous space, but for this product it is.
Thank you very much.
There's a famous class of surfaces which originates in Romania, and these are the Seika surfaces.
Yes.
Is there a concept for you? I mean, these are surfaces in affine geometry, but Seika's condition was formulated in Euclidean geometry.
Exactly.
Like yours. I mean, is there a connection?
The problem is to measure the first problem is to fix the origin and to measure the distance till the tangent plane. But sometimes it can be. I don't know here, but okay.
Are any of these affine spheres? An interesting question.
Yeah, maybe I'll think about it. Thank you.
Other questions? All right, let's make this bigger again.
Thank you. Thank you.